All right, this is our final unit of the semester. We're going to be looking at chapter 18, which is the laws of thermodynamics. So, the big ideas covered in this chapter are energy conservation and how it applies to thermodynamic systems, heat engines, entropy, and then the final law, which is the third law of thermodynamics. But we will cover all three of those. I guess technically four. Okay, so the zeroth law of thermodynamics is something that we have already talked about in a previous unit, but I just wanted to quickly recap it here in case you have forgotten. So the zeroth law tells us that when objects A and B are in thermal equilibrium and objects B and C are in thermal equilibrium, that if we were to place A and C in contact with each other, they would also be in thermal equilibrium. That's all it says. Okay. And now we'll move into the first law of thermodynamics, and we will be on this one for quite a few slides. So the first law of thermo is about the conservation of energy. And when we add heat to a constant volume system, so the volume is not changing, but we're adding heat, the internal energy, which is U of the system, will increase. Why? Because heat is a form of energy. So we can say that the change in the internal energy of the system is just equal to Q. A system will either do work on the surroundings or the surroundings are going to do work on the system. When the system is the one doing work on the surroundings, so the system does work on the surroundings, the internal energy decreases. So the internal energy of the system, of this system, decreases because there is no heat being added to the system. That means whatever our change in the internal energy is going to be equal to a negative value for work. Okay, so knowing that, we can actually look at the sign conventions for Q and W, so heat and work. We can look here. If Q is positive, it means our system has gained heat. If it's negative, the system has lost heat. If work is positive, then the work was done by the system. And if work is negative, work was done on this system. These are going to be really important to remember when you're working problems. It is so easy to miss a negative sign and then find your calculation is wrong at the end. So please make note of this. Put this on your formula chart. This is going to be very important as you're working the thermodynamics problems. Combining all of this information, we actually find a very simple equation for the first law, and that's just that the change in internal energy is equal to Q minus W, so heat minus work. That's it. Just keep in mind these sign conventions because they will trip you up when you're doing the math. As we discussed in the previous chapter, the internal energy of a system depends only on the temperature of that system. However, the work done and the heat either added or removed are going to be dependent upon the specific circumstances surrounding a process. And for this course, we're going to go ahead and assume two things about thermal processes. All thermal processes are quasi-static. That's a term you should commit to memory. That just means that they occur slowly enough that the system always remains in equilibrium. The second thing we assume is that all thermal processes are reversible, meaning that we can change them back to their original states. In this example of an ideal reversible process, we can see that compressing and then expanding a gas at constant temperature, so the temperature is constant in both of these, we compress the gas and then we expand the gas, it's going to result in the system returning back to its original state. So this would be a perfectly reversible process. Since our temperature is constant in this example, the compression is going to result in heat leaving the system, and the expansion will result in heat being added to the system. And that is because this is a constant temperature system. So to keep the same temperature, if we're compressing it, we've got to get rid of some heat. And if we are expanding it, we're going to have to add a little bit more heat to make sure our temperature stays the same. And in this example, we are assuming that this piston is frictionless. When work is done on a gas by expanding it, so when work is done on a gas, we are expanding it at a constant pressure. We see the following relationship between work, pressure, and volume. So work is equal to the pressure times the change in the volume. And this is at a constant pressure. Here is what a curve would look like for a constant pressure system. And this is pretty easy to figure out. And this area right here would actually be the work done. So whatever is under this curve, under this line, this is our work. And here it will be very easy to calculate because it's a nice rectangle and we know how to find the area of a rectangle. Now, when we have a constant volume system, so the volume is not changing. The volume of the gas is not changing. There is no movement being done, which means that no work is done. So our work equals 0 in a constant volume system. And our graph would just be a line. When it's the gas temperature that's held constant, this is what we're going to call an isothermal system. Isothermal system. So when the temperature is constant, we're going to see the pressure and the volume have an indirect or an inverse relationship, meaning as one is increasing, the other is decreasing. So if the pressure is increasing, then we're seeing a decrease in volume. And this is what a typical graph would look like for a constant temperature system. In that constant temperature system, the work done is still equal to the area under the curve. This one just won't be quite as straightforward to calculate. So in the previous a few slides ago, let's see, in this slide, this was simple to calculate because it was a rectangle. Now here, it's going to get a little bit more complicated in this isothermal system. There's the word isothermal system. This can be found with the formula here. So you see it's more complicated, where Ln stands for natural log, and you'll see that function on any scientific calculator. Another term you will want to commit to memory is adiabatic. And adiabatic just means some process where no heat flows into the system or out of the system. So no heat is escaping the system or coming into the system. The heat is constant. This is something that can easily be done by insulating a system, sort of like we did with those calorimeters in the final lab. The curve for an adiabatic process is very similar to an isothermal curve that we saw in this slide. And we will look at one. Okay, and here is a summary. Oh, I'm sorry. Aside from insulating the system, we have one more thing that we could do. So we can insulate the system, or in order to make it adiabatic, we could simply make sure that our change in volume occurs so quickly that heat doesn't even have time to escape the system or come into it. So it either has to be a rapid change in volume, or we're going to have to insulate the system. And here is a summary of those processes. So if it's constant pressure, we have this, and here's our Q value, constant volume, isothermal, and adiabatic. And this is something else you will absolutely want to have in your notes. Constant volume and constant pressure systems have unique specific heats as well. So for a constant volume system, we can find the specific heat by just dividing. Oh, y'all can't see that very well. I should not have put it there. Okay, there it is. So for a constant volume system, we can just divide our Q, and QV means heat in a constant volume system. Divide that by the moles of the gas present times the change in temperature. And that's how we would find our specific heat for that constant volume system. And the only difference we're going to see in the constant pressure system is we're now working with QP and CP. So the formula is going to be the same to find the specific heat of the constant pressure system, but we'll be looking at the heat for the constant pressure system instead of the heat for the constant volume system, and those will be different. We're not going to get into the derivations here, but the CV and the CP, so the specific heat for constant volume and for constant pressure for a monatomic gas, this is important, it's for a monatomic ideal gas, can be found by using these equations as well. So we have a couple of different ways we can do it this way, depending on the information we're given, or we can do it this way. And these are actually related by the R value, which you'll probably remember from the unit where we talked about gases. And we talked about the ideal gas equation. So the constant pressure specific heat minus the constant volume specific heat is going to give us that R value. But again, we're not going to get into this derivation here. And even though these calculations, the CP minus CV is for a monatomic gas, we can go ahead and apply that to a few other gases as well. So this would be monatomic because it's helium. This is not a single atom, but it's the same atom bonded twice, so N2O2. Argon would be a single atom system, a monatomic gas. Carbon dioxide is CO2, and methane is CH4. But we can also apply that to several other types of gas, and it works pretty well for real gases as well as those monatomic ones. I mentioned earlier that the PV curve, that pressure volume curve for an adiabatic process, is very similar to that of the isothermal process. And we can actually see that here. So we will signify an adiabat or an adiabatic process with this symbol. So if you see this, we know we're working with an adiabatic process. And this is some constant. This is just equal to CP divided by CV. So that constant pressure specific heat divided by the constant volume specific heat, which if we don't have, we can find in this way, and it's going to equal 5/3. So we don't even need any values here. We see here that this is equal to 5/3. And this is for a monatomic gas, but we saw that we can apply it to a few other types of gases as well, real gases. Oh, I'm sorry. So here we can see that this adiabatic system is very similar to the isothermal system. And we have another isothermal system here, but this is the adiabat. So an adiabatic system, we're going to see a steeper curve than in an isothermal system, and that'll be the main difference. And we've made it to the second law. So the second law tells us that spontaneous heat flow is always going to occur from the high temperature object to the low temperature object. So heat will flow from the hot object to the cold object. But we're going to take a look at how the second law is used in several processes. So let's start with the heat engine. This is just a device which is going to convert heat into work. And this is something that steam engines do. We see in a steam engine that fuel is going to heat water. So fuel will heat the water. And once that water has been heated, it's going to become a vapor. It's going to turn into a gas. And as it turns into a gas, it's going to expand. When it expands, it's going to do work on the system or on the piston. So it'll do work on the piston as this water is turning into steam. And then the vapor will condense back into. Okay, so once the vapor has done work on the piston, it's going to condense back into water, and then this cycle will just repeat itself over and over and over again. So that's how a steam engine works, just in a nutshell. Heat engines are all going to have three things in common. They're going to have a hot reservoir, they're going to have a cold reservoir, and they're also going to have some kind of cyclical engine. And we can see that right here. So these are the three things that all heat engines will have. In a heat engine, some amount of heat is going to be provided by the hot reservoir, and I can go back and show that here. So some amount of heat will be provided by this hot reservoir. And then some of that is going to be converted into actual work, and some is going to be given off as exhaust heat to our cold reservoir. So not all of it will be converted into work. That relationship can be seen here. So work is going to be equal to whatever the heat supplied from the hot reservoir is minus the heat supplied from the cold reservoir. And we can find the efficiency of any heat engine through this equation. So we're just going to take the work divided by the heat provided from the hot reservoir, and that's going to tell us our engine efficiency. There is another way that we can also find the efficiency of our engine. So efficiency, we know, equals this. Making a couple of substitutions, we know that work is equal to QH minus QC. We can actually find that the efficiency of a heat engine is 1 minus QC divided by QH. So in order for an engine to actually run, we must have a temperature difference between the hot reservoir and the cold reservoir. If not, no heat can be transferred, which means no work could be done. Just like with most things, we always need some example of a perfect system. And here, our maximum efficiency heat engine is going to be described in Carnot's engine. It's a man named Carnot. He kind of thought this up. Obviously, it's not possible to have a perfect heat engine, but it's a good basis for any calculations that we do or when we're striving to make the best heat engine possible. So he said that a maximum efficiency engine is one where the processes are reversible and that any engine must have the same temperature hot and I'm sorry, hold on. Any engine, so it doesn't matter if I have 40 different heat engines, if they have the same hot and cold temperature reservoir temperatures, then their efficiency will be exactly the same regardless of the process used. We clearly know that this is just a basis for designing heat engines, and it's not something that is possible to achieve. So we cannot make a heat engine that is perfectly reversible. That is not possible. Since the efficiency depends on our hot and cold reservoir temperatures, it's the ratio of those temperatures that's also equal to the ratio of heat transferred. And so we can find the maximum efficiency a heat engine could possibly have by subtracting the cold temperature divided by the hot temperature, subtracting that from 1. So we have several different ways that we can look for the efficiency of an engine, and it all depends on which information we have been given. So what information do we have access to? And we can use that to determine which efficiency formula we should use. But notice this is maximum efficiency and not just efficiency like this one was or this one was. So this means that the maximum amount of work that a heat engine could do is this. It's the maximum efficiency multiplied by the heat supplied by the hot reservoir, or making a substitution, it would be 1 minus the cold temperature divided by the hot temperature multiplied by that QH. If we have two reservoirs that are at the same temperature, so the hot and cold reservoir are at the exact same temperature, our efficiency would be 0. However, the smaller our ratio of cold to hot, the closer our efficiency is going to be to 1. So we want to have a large difference between our hot reservoir and our cold reservoir in order to have the highest efficiency possible. Even though spontaneous heat flow is from hot to cold, we can create an engine which does the exact opposite. And in fact, this is exactly what air conditioners and refrigerators do. A heat pump transfers heat from a cold object to a hot object as well. So we see that refrigerators, air conditioners, and heat pumps are sort of just backwards heat engines, if that makes sense. Okay, so if we compare a refrigerator to a heat engine, as I mentioned in the previous slide, we can see that the refrigerator is basically just a heat engine that's running in reverse. It uses work, so the refrigerator uses work to remove heat from the cold reservoir. So it's taking heat away from the cold reservoir and giving off that heat. So that is why behind a refrigerator, it's going to feel warm, but inside the refrigerator, it feels cold. And an interesting fact is that refrigerators actually give off more heat to the kitchen than they remove from the refrigerator. So from the inside of the refrigerator. And we can, again, just use the relationship between work and the heat to see this. An ideal refrigerator would remove a very large amount of heat from the refrigerator while needing only a small amount of work to do so. So that ratio of the work needed to the heat from the cold reservoir is known as the coefficient of performance, or the COP, and we can find that through this equation. Most refrigerators are going to have a value somewhere between 2 and 6, but the larger the COP, the more, ideal that refrigerator would be. Okay. And an air conditioner, honestly, it works very similarly to a refrigerator. That is why we actually keep the AC unit outdoors, because the amount of heat that AC unit is giving off would just result in it heating the house up instead of cooling it down. So we keep the AC unit outside because of the amount of heat it gives off while it's removing the heat from the inside of the house, therefore lowering the temperature inside of the house. But it works the same way as a refrigerator does. It's going to take in work and it's going to, from the cold reservoir, we're going to see the heat being transferred. Work is going to be done and it's going to remove that heat to the outside, which is going to be what our hot reservoir is. So the hot reservoir is just whichever one has the higher temperature. The cold reservoir is whatever has the colder temperature. It doesn't have to be an actual process. I mean, we see here that this hot reservoir is simply the outside. Okay. And then finally, we have a heat pump, and it works the same as an air conditioner, does. However, the process is reversed. So the cold reservoir would be located outside instead of the hot reservoir being located outside. And heat would be removed from the cold reservoir in order to heat the home. So in this case, the work that the pump is doing, it actually contributes to the desired results instead of taking away from it, which is beneficial. So it keeps the house warm, which is what we want it to do. So it doesn't matter if the thing giving off heat is located inside the house, because the whole goal of a heat pump is to raise the temperature inside the house. Okay, and then we also have an ideal heat pump, And in an ideal heat pump, that Carnot relationship is still true. The work necessary to add some amount of heat to a room is going to be shown here. So here we go. And we've just rearranged this equation, made a couple of substitutions to find this. But that coefficient of performance for a heat pump can be found here. So for a refrigerator, it was the QC divided by W. But here, for a heat pump, it's the QH divided by W. And you'll want to make sure you note the difference between those two formulas. So the transferred heat and the reservoir temperature. So here's the heat that's transferred between the hot and the cold reservoirs, and here is the temperature of the hot and the cold reservoirs. If we rearrange this equation to put the cold temperatures information on one side and the hot temperature information on the other, we see this quantity called Q divided by T. And that actually has a name. It is entropy. And entropy is shown with the symbol capital S. So delta S is the change in entropy, and it is just equal to Q divided by T, which the units are joules per Kelvin. So for entropy, for this definition of entropy to be true, our heat transfer has to be reversible. And we know that, well, I guess you don't know, I'm telling you right now, in any reversible heat engine, our entropy will not change. So in a reversible heat engine, entropy does not change. But in a real engine, which is what we're working with here in this universe, the efficiency is going to be lower than that of a reversible ideal engine. In other words, less heat is successfully converted to work. So that gives the following definition for entropy. So this is slightly more complicated. An important piece of information is that in an irreversible process, so a real process, we will always see the entropy of the system increase. Always. That means that the universe's total entropy increases when any irreversible process occurs. The universe's entropy is going to remain unchanged, though, when a reversible process occurs. But since all real processes are irreversible, the entropy of the universe is always going to be increasing. Even if a system's entropy decreases because of the work done on it, an even larger entropy increase is going to occur somewhere outside the system. So in any real process, which is what we work with here in this universe, we will always see an increase in entropy. As the entropy of the universe increases, the ability that the universe has to do work is going to decrease. So the heat given off during any irreversible process, during any real process, can never be gotten back because recovering that heat is impossible. It's impossible because to do so, we would need to see a decrease in the entropy of the universe, which, again, is not possible. We're always going to see an increase. Okay, so I showed you some definitions, not definitions, but equations that you could use to calculate the entropy increase or entropy in general. But what exactly is it? So the most popular definition of entropy is it's the order of a system, how much order a system has or how much disorder a system has. Increasing entropy means a system is becoming more disordered. And when I say disorder, I mean more chaotic, and I kind of put that in quotes, chaotic. I'm not sure if that's a great term, but more chaotic movements of the particles within a system. So at the micro level, not at the macro level, we're talking about how the molecules are moving around. I'm going to post a short video which provides you a much better understanding of what entropy really is and I actually like it better than what the book says as well. But ultimately, the ordering of a system, so how ordered or disordered a system is, all boils down to the probability that that system is in a particular microstate. And again, that video does an excellent job of explaining it and breaking it down for everyone to understand. Considering all of our previous statements that the universe's entropy is constantly increasing, that means someday it's going to be impossible for any further work to be done in this universe, which means that life won't be possible. This is actually what is referred to as the heat death of the universe, because as processes are giving off heat, it's increasing the entropy, which then decreases the universe's ability to do work. So that's a interesting and slightly terrifying fact. But if we're always moving towards a more disordered universe, a universe that has higher entropy, how is life even possible? Because we know that life can be created. We know that we start with one cell and then we move to an entire human being, which is clearly more ordered, and I'm putting that in quotes, ordered than just the single cell. But this isn't actually true. This isn't true. This isn't due to entropy, though, and it's instead due to energy. So life uses energy to be created and to grow and to thrive. All of those things, anything that's requiring energy, is an irreversible process. And those processes are still going to result in heat being given off, which is going to increase the entropy of the universe. And when that living being dies, it's going to stop using energy, but the entropy is going to increase rather quickly for that particular system. And I'm referring to the whatever this dead organism is as a system. And finally, we've made it to the third law of thermodynamics. This one's short and sweet. So it just tells us that we cannot lower the temperature of an object to absolute zero. We can get really, really, really close to absolute zero, but even in experiments, we've never managed to bring an object to 0 Kelvin. So here it states that it's something we can't do in a finite number of steps, and you can just imagine this scenario. So let's say you're walking towards a wall, and you're always moving half of your distance to the wall. So you're 10 feet away, and then you move half the distance, which is 5 feet away from the wall, and then 2.5 feet, and then 1.25, and so on. You will never actually reach that wall because you're always just taking these half steps. It would be impossible. And the same can be said here. If we lower something's temperature by half each time, yes, we can get really, really, really close to zero, but we will never truly hit absolute zero. And that's all the third law of thermodynamics states. Okay, everything else here is just a summary, so you can go back and look at the summary notes. I know this was a long video, so thank y'all for watching. And if you have any questions, don't know what happened here. As always, please post in the discussion board or directly email me. I hope you all have a great day. Thanks.